If you pick a single arbitrary vector in a vector space, how much of the underlying geometry of a linear transformation can that one vector reveal? This diagram shows what happens when we repeatedly apply a transformation, let's call it t, to a starting vector, v. We get t of v, then t squared of v, and so on. These vectors fan out, spanning a distinct geometric plane. We call this the t-cyclic subspace generated by v. Because any further applications of t just keep churning out vectors inside this exact same plane, we have isolated a self-contained, independent block within the larger vector space. Since we are working in finite dimensions, this fanning out process cannot go on forever. Eventually, the sequence hits a structural wall, where a newly generated vector bends back and becomes linearly dependent on the ones that came before it. We can write this structural wall as an algebraic equation, where a combination of our transformed vectors equals 0. By factoring out the vector v, we get a specific polynomial that evaluates to 0, known as the t-annihilator. The annihilator gives us two exact measurements. Its degree tells us the dimension of our cyclic subspace, and the sequence of vectors we generated up to that point forms a basis that naturally spans that space. The annihilator polynomial acts as the mathematical boundary that stops or kills our vector sequence. Now we have a specific cyclic subspace and a basis to match. To make this useful for computation, we need to translate this setup into a standardized matrix format. This k by k grid represents what we call a companion matrix. Notice how the subdiagonal is populated entirely by ones. Each one represents the clean shift from one basis vector to the next. For instance, t of v1 simply yields v2. But look at the final column. Instead of a clean shift, we fill the final column with the negative coefficients from our annihilator polynomial. Our final basis vector has hit that structural wall and must loop back into the space as a linear combination of the previous vectors. The companion matrix is the annihilator polynomial expressed as a grid, directly mapping the cycle of our basis vectors. Generating a single cyclic subspace isolates one behavior, but what if our initial cycle does not cover the entirety of our vector space V? This diagram shows the cyclic decomposition theorem at work. Any total space, V, can be partitioned into a direct sum of independent, non-overlapping cyclic subspaces. These blocks follow a strict divisibility rule. Each subsequent annihilator polynomial, or invariant factor, must completely divide the previous one. With P2 nesting inside P1, we can identify P1 as the minimal polynomial of the entire space. Tiling these companion matrices together along a diagonal creates the rational canonical form. We call it rational because the entire map is built using only basic arithmetic, addition and division, on the original matrix entries. This allows us to decompose the transformation without ever needing to solve for complex roots. Let's apply this. This 3x3 grid represents a matrix transformation T, paired with its factored minimal polynomial, x minus 1 times x minus 2. Because the minimal polynomial has a degree of 2, our first standard basis vector generates a two-dimensional cyclic subspace. The corresponding 2x2 companion block locks into the top left corner of our master matrix frame. Now we need to cover the rest of the volume. Pause the video and try to find a second vector, disjoint from our first space, that satisfies the remaining eigenvector condition, t of v2 equals 2 times v2. In our specific example, the first subspace occupied a plane where the third coordinate was always 3 times the second. To find our next vector, we look for a characteristic vector that breaks that rule. The coordinates 2, 1, 0 work. They describe a vector outside our first plane that still follows our target behavior, allowing the final 1x1 block to lock into place. The rational form organized a complex three-dimensional transformation into distinct behavioral blocks without relying on complex roots. We started at the micro level, watching how repeatedly transforming a single vector builds a cyclic subspace. We translated that sequence into algebra, using the annihilator polynomial to calculate the boundaries of the cycle. At the macro level, the rational canonical form organizes those cycles into a structured block diagonal matrix. The methodology and theorems we use today come straight from Chapter 7 of Hoffman and Kunze's linear algebra. If this step-by-step breakdown helped you, please subscribe and leave a like to support more math deep dives.